Today we're going to talk about our first asymmetric cryptographic primitive, public key encryption. So you'll recall that the difference, this is going back now all the way to the very first lecture, that the difference between the symmetric setting and the asymmetric setting is that in the symmetric setting, the communicating parties share a secret. So the information that they hold is symmetric in a sense. The asymmetric setting, as the name suggests, is one in which the communicating parties hold different pieces of information. And in practice, nobody actually calls it asymmetric cryptography. They talk about public key encryption and digital signature schemes. So today we're going to talk about public key encryption, and most people seem to already have the intuition for how for what public key encryption is. They know that rather than there being a single object called the key, which is shared between communicating parties, instead the key is somehow split into two pieces. One is a piece that is public and that can be freely released to everyone to use. And then the other piece is secret. And that's because in the asymmetric setting, we typically have use cases where there are operations that only the person who generated the key pair should be able to carry out. And those operations are going to be enabled by holding the secret key. So there are operations that we're going to allow everyone to carry out by use of the public key, and then operations that only the person who generated the key can carry out via use of the secret key. So let's just dive right in here. A public key encryption scheme, this is our syntax, is a triple of algorithms. Here we're using the same capital Pi notation for primitives. This is a difference from the symmetric setting where we had two algorithms, encryption and decryption, and an associated key space. Now we have a triple of algorithms, because there won't be a single well-defined key space anymore from which we can say one would sample. Instead, we're going to have an algorithm that's going to return keys for us. Associated to a public key encryption scheme is a security parameter, lambda, and this is just a number, a natural number. And security parameter you can think of as being a knob that you can easily tune in order to change the security properties, the concrete security properties of the thing that you build. Typically, this ends up being something like the size of the public or secret key, which in fact will translate into things like the size of some underlying group, the order of some underlying group. We didn't have this in the symmetric setting because it really wouldn't make a lot of sense. It's in the public key setting or the asymmetric setting where we're using these number theoretic or group theoretic hardness problems from which to bootstrap security. It's quite easy if you think about, for example, the Diffie-Hellman key exchange, to imagine carrying out the Diffie-Hellman key exchange over groups of different sizes, because the underlying group is just specified by a generator, and it's quite an easy thing to swap out some underlying algebraic or number theoretic object, and by swapping out, potentially change the provable security properties of the key exchange. The same will be true in a moment, as we'll see, for public key encryption schemes that are built on top of symmetric groups. In the symmetric setting, this wouldn't have made a lot of sense because there's nothing that you can naturally swap out. I mean, you can talk about having a block cipher mode of operation and swapping out one block cipher for another, but as soon as you swap something out, it's, like the key sizes and the input-output sizes are fixed. So even for something like AES where there are 3 permitted key sizes, it still doesn't really make a lot of sense to have a security parameter, because security parameter, the intuition is it's something that you can change in small steps and almost arbitrarily to make it arbitrarily large numbers. So we can easily go from a group of order, 128 to a group of order 256 to a group of order 512, or even things in between there. So there's kind of a continuous and easily tunable knob having the security parameter present in the public key setting. Anyway, the first of these 3 algorithms is the key generation algorithm, and this is new. Whereas before we would have just said there's some associated key set that we sample from, here we actually have an algorithm. We use the same calligraphic K to denote the algorithm that we used in the symmetric setting for the set. It takes as input the security parameter, and this is a way of signaling to the key generation algorithm, I need a public key or secret key of this size, or compute a public key secret key that's appropriate for this security parameter. The public key secret key pair that are returned by this randomized algorithm each come from underlying key spaces. So the public key comes from this capital P, capital K public key space, which is a function of the parameter lambda. Likewise, the secret key comes from its own secret key space, which is a function of the parameter lambda. So key generation is run. It outputs a public key, secret key pair. And we'll talk about how one uses that shortly. But the use of what operations are enabled by the public key and the secret key is going to depend on the primitive that you're actually trying to build. All right, the second of the three algorithms in public key encryption is the randomized encryption algorithm. And I note here that this is randomized because this is, again, a departure from the symmetric setting. In the symmetric setting, we said, well, encryption is deterministic, but it has this input called the IV. And this is the way in our security notions that we were able to enable per message variability or per encryption variability, so that if you were to encrypt the same message twice, you would get different ciphertexts with very high probability. We'll need the same kind of thing in the public key setting because we'll see that the security notion is still IND-CPA. It's just adapted from the symmetric to the public key setting. So the way we get it in the public key setting is we actually allow our encryption scheme, our encryption algorithm to be randomized. And we don't actually show the randomness as part of the syntax of encryption. We just understand that encryption takes some inputs, which we'll name, but then once those inputs are specified, the encryption algorithm itself is allowed to flip coins internally or use randomness in order to determine how to turn those inputs into a ciphertext. The inputs to encryption are, first of all, the public key. So the public key here, syntactically, we're saying it comes from the union of these possible public key spaces, where the union has taken over all possible settings of the security parameter. But you can think of it as it takes a public key that's appropriate for the security parameter. It takes in a plain text, which syntactically we'll think of as being a bit string, and it outputs a ciphertext, which we'll likewise think of as being a bit string, or this distinguished error symbol bottom. This will allow encryption the ability to complain if for some reason the plain text is inappropriate for, say, the underlying group that's being used. We formalize syntactically encryption as taking in bit strings and outputting bit strings, but more often we'll end up talking about encryption in terms of the native representation of the things that are being encrypted. So we'll see, for example, when one is building an encryption scheme whose security is based upon the hardness of some underlying cyclic group, then the plain text are actually going to be group elements. Of course, one couldn't always encode these as bit strings, but it will often be easier. We could make a more complicated syntax here where the plain text space also depends on the security parameter and other things, but it seems it's just cleaner since we typically won't have to refer to the syntax anyway, just to think of encryption as taking in bit strings and outputting bit strings. But that when we actually describe the encryption schemes, we'll often talk about plain text in terms of whatever the native representation is. In any event, our shorthand notation again is going to be as it was before. Encryption runs taking the public key as input and some plain text M, and here observe that we're allowing encryption to be randomized, so we put the $ over the assignment arrow, and it outputs some ciphertext C. The decryption algorithm remains deterministic as it was in the symmetric setting. It takes in the secret key, so again we take in a secret key from the union of all possible secret keys that are allowed for the security parameter. And it takes in a ciphertext and it outputs either a plain text or again this distinguished error symbol bottom. And we're going to use the notation we used before, but observe that decryption takes in the secret key, whereas encryption takes in the public key. So this should already suggest to you, when you think about how this is going to be deployed, if the public key is truly going to be public so that everyone can see it, that means that everyone is potentially going to be able to create valid ciphertexts, but only the holder of the secret key component should be able to decrypt those ciphertexts. For correctness, we require kind of the obvious thing, and that is that for every security parameter, no matter how you set the security parameter, and for every message that you might want to encrypt, if we run this experiment where we run the key generation algorithm to get a public key and a secret key, And then for whatever was the message M that we fixed, we encrypt that message M under the public key to get a ciphertext. If we condition upon the ciphertext not being bottom, meaning we actually do get a ciphertext being produced, then it has to be the case that if we decrypt that ciphertext under the secret key that corresponds to the public key that was used to encrypt, then we get back the message. This is very similar to what we had in the symmetric setting. It's just we have to adapt to the fact that now encryption uses a public key and decryption uses a secret key. We need this event, that decrypting a ciphertext C that was created under this public key. If we decrypt it using the secret key that's associated to that public key, then we get back the message. We need that kind of invertibility, if you will, to hold with probability 1, meaning it's always correct. Conditioned on the fact that encryption didn't say, no, this is an invalid ciphertext, because there we don't require the decryption to do anything. Okay, so let's look at an example of this. So here's an example public key encryption scheme. We're going to build this upon a cyclic group. So we've got a cyclic group G whose order is n, and we're saying that the order is the security parameter. And we're going to let little g be a generator of that cyclic group. Essentially, this encryption scheme, this is called the El-Gamal encryption scheme. And it's kind of a shame. This is essentially just the Diffie-Hellman key exchange turned into an encryption scheme in a very simple way. And it's almost a shame that Diffie and Hellman didn't just propose this as part of their paper, because that would have been the Diffie-Hellman encryption scheme. But nonetheless, this is the El-Gamal. It's named after Thomas El-Gamal encryption scheme. So it really is going to look very much like the Diffie-Hellman key exchange. Key generation works by first picking an exponent x out of the numbers between 0 and n-1. Recall that n is going to be the order of the group. So we're really just picking an exponent x as we did. This is like Alice picking her exponent. The public key is then going to become g to the x. That's what everybody's going to get to see. The secret key is going to be x, or the discrete log of the public key. And then we'll output that public key secret key pair. Encryption takes in the public key and a message. And this message is going to be naturally thought of as being an element of the group G. And we'll see why. To encrypt a message M, we first pick an exponent r, again from the integers mod n. We're going to create r as g to the r. Capital R is g to the r. So look what we have. We have the public key is g to the x, and to encrypt now we have a g to the r, which is sort of like Bob's side of the exchange. The key then becomes the public key raised to the r, which we observe is just g to the x raised to the r, or g to the xr. So this is just like it was in the Diffie-Hellman key exchange. What we return then is r. This is the per message randomness, right? This is picked fresh each time we encrypt. So the per message randomness is encoded into this capital R. We'll send that because we're going to need it on the receiver side to decrypt. And then the actual encryption, if you will, is to take the key, which is g to the xr. You take the key, and we multiply it. Or we're going to apply the group operation, but we've used this cyclic. We've talked about cyclic groups where the operation is multiplication, so that's naturally why I say multiply. But it's whatever the underlying group operation is. But if we think of multiplication, like doing this over z star p or the quadratic residues, to encrypt, you take the key and you apply the group, you multiply it times the message. And I note here that the key is g to the xr, and the message, because it's a group element, is g to the a for some a. So really what we're getting for sort of the encryption part of this is g to the xr plus a up in the exponent. Okay, for decryption, how does it work? Well, to decrypt, we're going to split the ciphertext into two pieces, R and C, because it has two pieces anyway when we encrypt it. And we're going to regenerate the key by taking R, which is G to the little r, and raising it to the secret key. Well, the secret key is X, so we indeed again get that the key is G to the XR, just as we did on the encryption side. To recover the message, we take the inverse of the group element G to the XR. And because we're in a group, we know every element's going to have an inverse. So we take the inverse of the group element that is the key, and we multiply that times the core ciphertext component C. And as I've shown here, that means you're taking g to the xr inverse, and you're multiplying it times what c is, which is g to the xr times m. Of course, the inverse, g to the xr inverse and g to the xr cancel, leaving us with m. So it's correct, and that's what we return as m. That's it. That's a very simple encryption algorithm that really is basically just the Diffie-Hellman key exchange almost directly translated into an encryption algorithm. And as soon as you see this written down, it's like, okay, this is it's clearly correct. It'll work over any cyclic group. So what security properties are going to be sufficient to argue that this encryption scheme is secure? Of course, there's a question we have to answer even before that, which is, what does security even mean for a public key encryption scheme? But we can sort of stare at this for a second and think, okay, what property would be sufficient? Well, we know property that would be necessary. For example, everyone sees the public key g to the x. So if you could compute the discrete log, then you could recover x from the public key, but x is the secret key, meaning now you could perform decryption at will. So clearly discrete log will have to be hard. Likewise, if somehow upon seeing the public key, which is g to the x, and a ciphertext, which is g to the r for a random r, and then this sort of core component, if upon seeing these, in particular the public key and the per message randomness capital R, so you have g to the x and g to the r, if from those you could compute g to the xr, which is the key, then you'd be able to decrypt again, right? But that corresponds to the computational Diffie-Hellman problem. Given a g to the x and a g to the r, compute g to the xr. So clearly, the CDH problem is going to have to be hard in the cyclic group in order for this to have security. Those are both going to be necessary, but they're not going to be sufficient. In fact, the decisional Diffie-Hellman problem is going to be sufficient for what we need to show security. But before we can do that, as I said, the first thing we have to do is define what it means for a public key encryption scheme to be secure. Okay, so let's have a look at what security means for a public key encryption scheme. And it's very similar to what we had in the symmetric setting. We have the indistinguishability of ciphertext under a chosen plaintext attack, or INDCPA. For a public key scheme, pi with a security parameter lambda is just the experiment given here. Of course, the adversary is assumed to know the scheme and the security parameter. The only thing it doesn't know is, well, the secret key, obviously, but we'll give it explicit inputs here. The experiment starts by key generation algorithm running using the security parameter and outputting a secret key, public key, secret key pair. And then we flip a bit. That's going to be the challenge bit that's going to determine the behavior of an oracle, as in the symmetric setting. And then we're going to give the adversary the public key as input, because everyone is able to have the public key. And we provided an oracle whose behavior is described on the right. The oracle takes two inputs, M0 and M1. And as in the symmetric setting, if M0 and M1, when thought of as bit strings, are different lengths, then we return bottom. Again, public key encryption, just like symmetric encryption, is not going to be required to hide the length of the underlying message. And what we return on this oracle is the encryption under the public key of message M sub b. The adversary's job is to try to guess what is the value of the challenge bit. In other words, as before, whether or not the left message or the right message is the one that's being encrypted. Because this is a bit guessing game, advantage is defined in the usual way. It's the probability that this experiment outputs 1, meaning that the adversary manages to guess the challenge bit, scaled by 2 and subtracted 1, and we track the running time, the number of queries, and the total length of those queries as the resources. Now, one thing you can ask yourself as you're looking at this is, well, hang on a second. If the oracle is returning the encryption under the public key of something, and the adversary itself has the public key, so why do we need the oracle at all? The adversary can just simply make up ciphertexts of its own. And that's true. And this is why the point of the oracle, obviously, is to give the challenge. The adversary can sit here offline with the public key and make up ciphertext that it wants. In the symmetric setting, when we wanted to do that, you had to, in both the left and the right message, ask the same message, right? That would allow you to see targeted plain text ciphertext pairs. Here, the adversary can do that automatically because it has the public key, and having the public key is all that one needs in order to produce ciphertext. So the point of the oracle is to provide the challenge to say, okay, even if you are able to make up your own valid ciphertexts and see them locally, you still should not be able to distinguish between, if you provide me a pair of messages, the encryption of the left message or the encryption of the right message. So this is IND-CPA for public key encryption schemes. Quite similar, except perhaps for this one distinction that the adversary gets the public key. But that's going to be pretty handy because it turns out that because of that, we actually have this quite handy result, which is that we can reduce thinking about, so the general IND-CPA notion allows for Q queries as in the symmetric setting. But we're going to want to build public encryption schemes like the one we just looked at, El-Gamal. We talked through this a bit and said, well, we're going to need least for discrete log and CDH to be hard. But what we're going to show is, in fact, that DDH is sufficient for this thing to meet our security notion. But if you think about the DDH security notion, also discrete log and CDH, those are single instance hardness notions in the sense that the adversary in those problems, think about CDH, for example. The adversary is provided as input g to the x and g to the y for a single x and y, right? It gets a g to the x, and it gets a g to the y, and needs to output g to the xy. That's a one instance problem, right? Given a g to the x and g to the y, output a g to the xy. Well, oops, I should stay here. If we were thinking about building, El-Gamal, and we're going to reduce the hardness of the security of El-Gamal to the hardness of, say, CDH, that means we're going to have to do a reduction where we have an adversary for IND-CPA for this scheme, and we're going to build from it another adversary for the CDH problem. And somehow, that reduction that we do is going to need to turn A's ability to break the IND-CPA security of this scheme into the ability to compute g to the xy. And you can sort of see the pieces are here, right? Here's g to the x, if you will, here's g to the y, there's g to the r. So there are natural places where a CDH adversary could embed the pieces of its inputs. Like you could imagine saying, oh, well, g to the x I'm going to use here when I simulate encryption, and g to the y I'm going to use here when I simulate ciphertext production. But it can only do that once because it only gets a single g to the x and a single g to the y. It doesn't get many. So then this raises a question if you say, well, okay, but if I'm allowing in the IND-CPA security notion, I'm allowing for an arbitrary number of queries q, then if I've only got one g to the x and one g to the y to use, how am I going to use them to simulate lots of ciphertexts? And the answer is we won't have to. And the reason we won't have to is, in fact, because the adversary gets the public key. So we have this handy result which says the following. If you have an adversary A for the IND-CPA experiment for attacking some public key encryption scheme, and that adversary asks Q queries, then there exists, not just exists, but you can construct a one query, a single query IND-CPA adversary B with this security bound. Namely, that the advantage that you get with Q queries is upper bounded by Q times the advantage you get with one query. This is somewhat intuitive, right? If I ask one query, then somehow multiplying the little bit of advantage I get by asking one query times Q ought to give us something like the advantage one would get by asking Q queries. So there is some useful intuition that's here. And in fact, the intuition behind this result, we won't actually do it. I'll post a separate set of notes to help explain it. But the intuition here is essentially that, well, both A and B. So B is getting to play, maybe I'll scroll this up a bit. B is getting to play, both A and B are playing this IND-CPA game, which means that B, our one query adversary, is getting the public key as input. But that means that B can simulate proper ciphertexts for A. So when A is asking queries, B can simulate proper ciphertext. So I say this here. Since B receives the public key's input, it can simulate ciphertext for Q minus 1, right? For Q minus 1 of A's queries. It's asking Q queries. For Q minus 1 of those queries, if you're a little bit clever, you can use the public key to properly simulate things. And for the remaining query, you choose which of the Q queries, you choose one of them. For that one and that one alone, B will actually take the left-right pair that it's handed and send it to its oracle, right? Both A and B are playing the same game. They're both playing IND-CPA. So what B will do is say, okay, I'll pick one of A's Q queries, one of these queries, and I'll send that to my oracle. And on all the rest of the Q minus 1 queries, I'll simulate those using the public key that I'm holding. I have to be a little clever about it. How does B figure out which of the queries to actually take and send up to its oracle in an attempt to win the game with a single query? Well, in a sense, we just have B kind of guess a number between 1 and Q, and say that number is, I don't know, I. And on the ith query, it will take that and send it to its oracle and then return the return value to A. And on everything else, it's going to simulate something using the public key. And the intuition for why this should work is this. So if delta is the advantage that A gets using Q queries, then loosely, in kind of like a, I don't know, pigeonhole or triangle inequality kind of sense, if you can get delta advantage by using Q queries, then that means that there's some query that's in there among those Q that again, loosely, gains advantage at least delta over Q. Why? Because if all of those queries were to build up advantage, each of them with less than delta over Q, then the sum over all of the Q queries, so it's like delta over Q plus delta over Q and so on, or something that's each of the sort of incremental advantages you get from a query, if each of that incremental advantage pieces were less than delta over Q, then the sum of those incremental pieces would not be delta. So that's the kind of intuition for where this comes from. If this here, well, I guess if delta is this number, then what B is going to try to do is guess which query is going to be the one that provides at least delta over Q incremental advantage, and it's going to use that one to send it to its oracle. And when you do the analysis, you can show that, if this is delta, then, if you move this Q over here, divide both sides by it, you get delta over Q on this side. So it's saying that B's advantage is at least going to be delta over Q. That's roughly the intuition for the proof. The actual proof is more complicated, and as I said, I'll just post a separate set of notes. I won't talk over them, but I'll post a set of notes so you can see exactly where this result comes from. But even if you don't invest the time to do that, this is the important piece, is that given a Q, if you want to know what the full-up Q query attack advantages of an adversary A in IND-CPA, it suffices to look at an adversary that makes a single query, and then just multiply that by Q to get the bound. And that's nice because a single query IND-CPA adversary, that thing could make use of a single instance of, say, CDH or DDH or discrete log. So by virtue of the fact that we have this, it's called many to one or 1 to Q to 1 sometimes. The fact that we can relate the Q query advantage to the 1 query advantage allows us then to naturally connect to the single instance hardness problems that we want to use. If that's not clear, do try to roll back a few minutes and listen to that again and see if it becomes clearer. All right, so indeed, let's go ahead and prove that Elgamal is secure under the DDH assumption. So we want to prove this informal statement, that if you have a triple here of a cyclic group with a generator G and the group's order is N, if that is DDH secure, meaning the DDH problem is hard to solve for efficient adversaries, then the Elgamal encryption scheme that we just looked at is IND-CPA secure for 1 query adversaries. And again, that's all we need to show, because we can take whatever bound we prove here, multiply that by q, and that gives us the q query bound. Okay, so to start, let's think about what we want to do here. So we want to say that if we have a DDH secure group, then Elgamal is IND-CPA for one query. So we're going to start with a one query adversary for the IND-CPA game, and we're going to build from that an adversary for DDH. So let's go ahead and do that reduction. This is a proof where we just start straight away with the reduction. I guess that's actually how we've done many of the proofs so far. So here's our adversary B for the DDH game, B. Remember, in DDH, you get x, y, z triple, where x is g to the little x for some random exponent x, y is g to the little y for some random exponent little y, and then z takes on one of two values. If the challenge bit in the DDH experiment is 1, then z is g to the xy. If the challenge bit is instead 0, then z is g to the little z for a random exponent z. And you'll recall that the adversary's job, B's job, is to guess whether or not the capital Z that it has received is g to the xy or g to the z for a random z. So again, what we're going to try to do is perfectly simulate what our one query IND-CPA adversary expects, which is the ability to have a challenge oracle to which it can make one query. So in the IND-CPA experiment up here, it's getting to make one query to this oracle. That's it. And that query is supposed to have returned to it the encryption of either the left message or right message under the encryption scheme using the public key, which in this case is the Elgamal encryption scheme. So B, our adversary B for DDH, needs to take its input and simulate this single query IND-CPA experiment where the oracle returns the Elgamal encryption of either the left or right message. So we're going to try to simulate that as closely as possible. So how do we do that? We start by flipping a bit D, which is going to determine whether or not we're going to encrypt a left or right message. We then run A. We provide A with the input X. Now remember, in the IND-CPA experiment, it gets the public key. Well, the public key for Elgamal is g to the x for a random exponent x. But that's exactly what B gets in X, right? So we can provide that to A as the public key, and that is the correct public key for Elgamal. So far so good. Now, when A asks its single query M0, M1, what we need to now do is return a ciphertext, the Elgamal ciphertext, of message M sub D, where D is the challenge bit that we picked. And to do so is quite straightforward. Here's M sub D, so we got that part taken care of. What we're going to do is, what are we supposed to return? Let's roll back up to Elgamal. We're supposed to, in Elgamal, pick a random R and then have G to the R. And G to the R is going to be the first part of the ciphertext. Well, if you look at what we have from our DDH experiment, we have this thing, right? This thing can play the role of capital R because it's just renaming, right? Y, little y, is a random exponent. Little r is a random exponent. You take g to the little y, that's the same as g to the little r. As long as the exponent's random, the distribution's the same. So we can actually use this in place of r, the per message randomness that we need for encryption. How about for the other piece of the Elgamal ciphertext? Well, we're supposed to take the public key raised to the r, but the public key is g to the x, so we need g to the xr, and we need to multiply that times the message. Okay, so in our reduction, what do we get? Well, we've used x and we've used y. We need to use z. And you'll notice that if the challenge bit in the DDH experiment is 1, then we actually get g to the xr with this renaming of y's becoming r's. We actually have a proper key for Elgamal. So what we should do is just take the z that we're given, multiply it times m sub d, and that's what we're going to return as our ciphertext. This is a properly formed Elgamal ciphertext. So long as we're only asked one query, this is a proper thing to do. Well, of course, in the case that the challenge bit in the DDH experiment is 0, we're instead going to get this g to the z behavior, but as we've seen in previous reductions that we've done, we're going to do our best to simulate perfectly when our challenge bit is 1, and when our challenge bit is 0, we're just going to hope that we don't, lose too much in the process. When A finishes, so A gets its single query, we return a proper elgamal, at least in the case that Z is G to the XY. This is a proper elgamal ciphertext. So we return this to A, and then A is eventually going to halt with a bit, right? The bit that's trying to guess whether the left message or the right message has been encrypted, and we're simply going to return whether or not it was correct. That's going to be our reduction. Why are we going to do this step of returning whether or not it guessed the message? Well, in some sense, because it's the obvious thing to do. It's what the IND-CPA experiment does, and we know that we should try to follow the experiment that we're trying to simulate. But also, as we've talked through, if we in fact are in this case, if we have G to the XY, then this ciphertext that we've produced is exactly the elgamal ciphertext for a message that is either the left message or the right message, depending on a random challenge bit. So this here is a perfect simulation of what A expects. In the IND-CPA game, which A expects to be playing, in which we are simulating for one query, the adversary wins if it guesses whether the left message or the right message has been encrypted. So that seems like a natural thing to do. And indeed, because of that, we can claim, we need to figure out what is the DDH advantage of the adversary we just built, the adversary B. So we know the DDH advantage is twice the probability that B wins the DDH game. And so as usual, we just take the probability of the event we care about, the fact that B wins the DDH game, and condition it on the challenge bit. So we've just said that if the challenge bit in the DDH game is 1, then B perfectly simulates the IND-CPA experiment for A when elgamal is the underlying encryption scheme. So this statement is pretty much obvious from what we just talked about. The remaining question then is, all right, well, what about the other case? What about the probability that when the challenge bit is 0? And here as before, we usually do this term here, you'd think more naturally, this should be a 1, and then I'll multiply these two things by a half each and add them together. But the usual thing we do is we say, oh, let's look at 1 minus this thing, right? That's how we analyze these things. And the reason we do that is because if the challenge bit is 0, the experiment outputs 0 when B does not output 0, which means that B outputs 1. B outputs 1 when A manages to win its game. So it's, again, kind of a more natural alignment, as we've done in all of our previous reductions along these lines. So this piece we've got, that's taken care of. We need to finish analyzing this piece. Let's see how that goes. All right, so let's talk through this. When the challenge bit is 0 in the DDH game, that means that Z is G to the Z for a uniform exponent Z. Okay, so that's the first thing to keep in mind. The second thing is over here, this event. When would the experiment output 0 when the challenge bit is 0? Well, it happens, as we just said, when B outputs 1. B outputs 1 exactly when A, given the public key, guesses the bit. Okay, so we're going to capture this probability in a very short sequence of games, as we did, for example, in the proof of counter mode. And in fact, this is going to be very similar to the proof of counter mode, and we'll see why. But I want to return to this thing. When the challenge bit is 0, that means G to the Z is a uniform group element. And if you think about the ciphertext that A gets in return, that ciphertext is either G to the Y, G to the Z times M0, or it's G to the Y, G to the Z times M1. We can think of M0, because it's a group element, as G to the A0 for some exponent A0. We don't have to even know what it is. It's just because it's a group element, we know we can write it as a generator raised to a power. So M0 we'll write as G to the A0, and M1 we'll write as G to the A1. So these are the two possibilities. If the bit that B flips is 0, then we get this case. If the bit that B flips is 1, we get this case. And what we notice, and we're going to see momentarily, is that the distribution of these two possibilities is the same. Let's see why that is. So we're going to make a game G0, which is going to perfectly capture this event here. So here's G0. So if you look at the IND CPA game for Elgamal, what happens? Well, you remember there's a little x, a little y, and a little z, and we're going to have a g to the x and a g to the y, and those are just going to be random group elements, right? This is g to the x, this is g to the y, or actually g to the r, I guess. And these two things are uniform group elements for sure, always. Now, what about this capital Z? Well, capital Z, in the case, since we're conditioning on the bit being 0, capital Z is itself a uniform group element. So we'll just go ahead and pick these three things uniformly from the group. So far, that's precisely the case here. Then we're going to flip the challenge bit, as we do in the IND-CPA experiment. We're going to give A an oracle that we'll describe in just a moment. A is going to get the public key as it did for input, and output a guess at the bit, and it's going to return whether or not it guessed the bit properly. What does this oracle do? When A asks its single query, it just returns what we returned in our reduction, y as the g to the r component, and then z times m sub d. Remember, that's exactly what we did here. Okay? So we can conclude that the probability of this event, conditioned on the challenge bit being 0, it's precisely the same as the probability that, right, sorry, I almost got confused there for a second. Right, so again, the probability that this event happens, in other words, that the DDH adversary we built B does not correctly guess its bit, given that its bit was 0, meaning that you have g to the z as a z element, the probability that B outputs 1, meaning the experiment returns 0, is precisely the probability that A guesses the challenge bit in its experiment. But its experiment we've just captured here, right? We've just captured the experiment that A is playing when B simulates for it, and the capital Z component of B's input is this random group element g to the z. We've just built this game G0, which exactly captures that. This game G0 outputs 1 when A manages to guess the left or right bit, which is precisely when our constructed B outputs 1. Right? So G0 is just capturing exactly this, but conditioned on this piece being uniformly random. That's all it is. So the B would lose the DDH experiment by outputting a 1, and it loses because the challenge bit is 0, precisely when A, playing this game G0, would output 1, right? B outputs 1 when A wins its game, so B outputs 1 when A wins its game. All right, so that's the first piece. This is just, as I say here, it's by construction. And if that's not clear, go back and look it over again. I think you'll be able to see it. All right, so now we're going to move from G0 over to this game G1. And what we're going to do here is we're going to start out the same way by picking capital X, capital Y, capital Z, all uniformly from the group. We'll flip our challenge bit. Everything else is the same. The one difference is here. Now over in G0, we actually returned Y and Z times M to the D. But what I want you to observe is the following. Let's look up here. If D is equal to 0, then Z times M sub 0 is just this, right? Now I've said M0 we can write as G to the A0 for some unknown A0. But what is the distribution of this product? Well, this is G to the Z plus A0 up in the exponent. But if Z is random, then Z plus A0 is random. So this is a uniform random group element. It's just a shifted uniform random group element. How about the distribution on this? If the message is in step 1, so if D is equal to 1, then Z times M sub 1 is this. But that's just G to the Z plus A1, where again Z is uniformly random, which means we still get a uniformly random element, just shifted slightly. So no matter the value of D, this is a uniformly random group element. Let me say that again. No matter the value of D, whether it's the left message or the right message, it doesn't matter, because when you take any group element and multiply it by a uniformly random group element, you get a uniformly random group element. So our oracle in G1, rather than returning z times m sub d, could just return z, because z is also a uniform group element. So the distribution, as I say here, the distribution of y comma z times m0 and y comma z times m1 and y comma z, they all have exactly the same distribution. Which means this oracle here can just return y comma z. But what can we do if the oracle is returning y, which is a uniform group element that's independent of the public key x, and z, which is another uniform group element that's independent of y and of z? Well, A could have just made up that response itself, right? It could have just picked it for itself, these things randomly. So what we can do, if we wanted to in a game G2, but we won't, is simply, because everything in this execution, if you look at all of this and the behavior of the oracle, everything is independent of the challenge bit D except this return statement. So we can do as we did in the proof of counter mode, which is to move D down there. And once that's the case, once you move the challenge bit D to after D runs, then it's clear that the chance that A manages to guess the challenge bit is a half. This is just like counter mode. Why? Why is that the case? Well, if you think about counter mode, said I've got the output of a PRF, so I've got this random n-bit string, and I XOR it with a block of n bits of message, and we concluded that, well, if I have n uniform bits and I XOR them with anything, whether it's n bits to the left message or the right message, I still get random bits. And because of that, we can move the challenge bit until after the adversary A runs. We're getting exactly the same behavior here. Because we're applying this group operation with a random group elements, because we're doing this and this was random, this is like saying I have a random, this is analogous to I have a random n-bit string coming out of my PRF. I have a random group element. My operation in the symmetric setting for counter mode was I take that random n-bit string and I XOR it with a message. Here I've got a random group element and I apply the group operation to an arbitrary other group element. This is kind of like counter mode, or maybe even more extreme. It's kind of like one-time pad, but in the cyclic group setting. That applying the group operation with a random group element, because of the properties of groups, gives us effectively the behavior of one-time pad. So El-Gamal is a very secure encryption scheme under the DDH assumption. So let's go ahead and finish this proof out. So now we want to know really what is the DDH advantage of B. And as we said before, we were looking at these two components. We pulled these out as the things that we needed to focus upon. We got answers to those, so now we're just going to stick those back in. So we've already said above that when the challenge bit is 1, then we perfectly simulate El-Gamal inside of the IND-CPA experiment. So we can make, we can replace this with this. This term over here we just argued is a half. So when we multiply through, so the 2's and the halves cancel. So we're left with this 1, and out here we have a -1, so those will cancel, these do cancel. So what we're left with is this thing, which is equivalent to that, and this thing, which is equivalent to a half. So that's just simple substitution and canceling. And then we do our usual trick of saying, well, the probability of the IND-CPA experiment outputting 1 is just half the advantage plus a half, just by moving the scaling by 2 and the -1 around. And so of course the positive half and the negative half cancel, and we're left with the DDH advantage is equal to half the IND-CPA advantage of our single query adversary A. And just by rearranging, we get this for a one query adversary A. Twice the DDH advantage of B is a bound on A's IND-CPA security. And then that means if we wanted to scale that up to a full Q query, we just use our 1 to Q result from earlier. And that means we have to multiply, well, remember we have to multiply this thing times, we said that the upper bound on this thing in the 1 query case is upper bounded by Q times, try this again. This is the Q query advantage for a Q query A. And we said in the previous result, this is upper bounded by Q times this, the one query, right? This is upper bounded by Q times this. But this and this are equivalent, so that means we have to multiply this by Q. So for a Q query adversary, we get this, that 2Q times the DDH advantage is upper bound on A's probability. And that's for the full up Q query adversary A. Cool, so we have our first provably secure public key encryption scheme under the assumption that the DDH problem is hard, and that shows up here, right? If the DDH problem is hard, that means this number is small for all reasonable B. If this is small, well, we have to look at this multiplicative factor. So the factor of 2 is not a big deal, right? 2 times small is an upper bound on something that's got to be small as well. How about this Q? This pops up because of this 1 to Q lemma that we employed. What does this actually mean? Well, okay, so Q, what is Q? Q is the number of challenge encryptions that the adversary sees. So this is like the number of public key ciphertext that an adversary might see when it's observing some communication. If that number Q is big, then what does that mean? In order to keep this whole left-hand side small, it means you have to make this even smaller. By making this thing smaller typically means you have to use a different group, a larger group. Usually you have to increase the value of the security parameter. So maybe you go from a 512-bit group to a 1024-bit group. If this number Q in your result is not going to be large, and oftentimes it won't be large because, as we've said before, public key encryption is not used to encrypt lots of ciphertext typically. Usually you use public key cryptography mostly to establish a symmetric key that then can be used to bulk encrypt lots of data. So if you're in a setting where the number of ciphertext that you're going to observe under a given public key is not too large, then maybe you don't have to mess around with the size of the group. But if you're in a setting where you're concerned that it might be large, then that tells you, okay, in order to keep this whole left-hand side small, I'm going to need to use a bigger group. And we already know that we have one candidate group in which this is hard, and that's the quadratic residues modulo prime P. So if you're expecting Q to be large, then that means you better pick a bigger P, a bigger prime P to use. All right, there's our first provably secure public key encryption scheme. Well, fine. So this says if you have a group, if you're operating in a cyclic group over which the DDH assumption is believed to hold, then Elgamal is IND-CPA. Great. But what if my group G is not DDH secure? Like what if I'm stuck working with Z star P instead of the quadratic residues mod P? Or what if I'm working in a group where the best known attacks for DDH suddenly get better, whereas the best known attacks for CDH don't? A DDH is a we're asking less of the adversary there, right? We're saying, give us one bit of information, whether or not you've got a valid Diffie-Hellman triple or a random Diffie-Hellman triple. CDH says, given g to the x and g to the y, compute g to the x, y, right? So let's say you have a group in which, because of the algebraic structure or whatever, DDH becomes less believable. Then you'd like to still say, perhaps, can I still use Elgamal? Do I have to change my encryption scheme? Or can I back off and say, okay, let me just assume CDH, where I'm asking more of the adversary. My DDH attacks got better, so I'm concerned about basing security on DDH. But CDH seems like it's still okay. So can I still use Elgamal? Or, in other words, as they say here, can I hedge? If the DDH attack is getting better, can I kind of hedge and say, all right, I only want to rely on CDH because I believe that that's a harder thing to do, to compute an entire g to the xy. I think that's harder than just guessing one bit of information. So can I just work from CDH? And the answer is yes, with a slightly modified construction, very slightly modified, and we're going to see it. Where the analysis is done in what's called the random oracle model. We've talked a little bit about that. We'll say more in just a second. So let's look at this slightly modified construction. This is called the hashed Elgamal scheme. So everything is basically the same. I've got a cyclic group G of order that's a security parameter, and I've got a generator. But now I'm going to add to that a hash function. I'm going to assume I have a hash function that maps group elements to group elements. And I'm going to employ the hash function. Everything in hashed Elgamal is the same as a normal Elgamal, except when I generate this per encryption key, rather than just using the public key raised to the R, which is G to the XR, I'm going to hash it. I'm going to take the public key raised to the R and hash it. And that's going to be my key. And likewise, on the receiver side, rather than taking this R, which is G to the R, and raising it to the secret key, which is X, remember in regular Elgamal, I would have gotten G to the XR over here. Now, to get the same key as I had for encryption, I hash it. That's the only change I make, going from Elgamal to hashed Elgamal. That's the addition of this hash. And if we model the hash function as being a public random function, so this is the random oracle model. Random oracle model is, and I'll actually post some additional notes about this, perhaps a whole video. To take INDCPA and turn it into INDCPA in the random oracle model, you simply take this experiment and you give the adversary an additional oracle for H. That's the change. In the random oracle model, all algorithms, you basically are hash function's a publicly computable thing, so everybody's going to be able to compute the hash, including the adversary. But we're going to model, in some sense, we're going to say, like, okay, let's say that the hash function is perfect, and that everybody treats it like a black box. Nobody looks at the structure of it. And the perfect behavior is you put in a distinct input, you get a random output. So it's basically it's a publicly computable random function. We provide it as an oracle to everybody. That's how you translate security notions into the random oracle. And this scheme is secure based on the CDH assumption. I actually see that I have a typo down here. This should not be DDH, but rather it should be CDH. CDH, yeah. The hashed Elgamal scheme is INDCPA when we model the hash function as being perfect, as being a random oracle. Hashed Elgamal is INDCPA against one query adversaries, only assuming that CDH is hard. And the way this is going to happen, and maybe I'll actually put up the proof for this too. The way this happens is essentially like the adversary is going to be able to make lots of hash computations itself, right? This is going to translate into calls to the hash oracle. But unless the adversary happens to call the hash oracle on G to the XR, then in some sense the hash oracle is kind of useless, because the hash oracle is only being used to turn public key to the R into the key that's being used for encryption. Otherwise, it's not being used anywhere. So it doesn't matter that the adversary can sit there and make lots of hash computations itself. They're all useless from the point of view of attacking Elgamal, unless it happens to make this particular hash call. And in particular, calls upon G to the XR, which, if you think about the CDH game, if this G to the X is my input and this G to the R's is my other input, what am I supposed to do in the CDH game? I'm supposed to compute then G to the XR. But unless the adversary calls the hash function on G to the XR, it can't win, basically. So what we're going to do is kind of say, okay, we're going to watch what queries the hash function makes. The adversary makes to the hash function. And if it ever manages to query upon G to the XR, then we can win, because that means that what it's done effectively is computed the CDH answer for us. That's going to be the rough intuition for that proof. The result you get is that a one query adversary's INDCPA advantage against hashed Elgamal, is upper bounded by the CDH advantage of an adversary that we build. We'll have this factor of 2 floating around like normal, and we're going to scale it by the number of hash queries that are made. That's the bound that we prove. What does this mean? Well, if you think about what this bound means, it says, all right, if I want this side to be small, so it's an upper bound on this. Well, now what am I doing? I'm scaling by the number of hash queries. And in fact, if we were to scale this all the way up to a Q query adversary A, we'd have an extra factor of Q over here, which is the number of encryption queries that are made. even if the number of encryption queries is small, so in this case we're looking at the one query adversary A. Even here, it's a little concerning, right? We're demanding less, so we're kind of getting away with a little less in terms of what we demand of the group that we use. But there's no free lunch because now we're scaling by the number of hash queries that are being made. Hash queries are equivalent to like local hash computations. This number could be quite big. That's, even if the number of encryptions that you see is small, the number of local hash computations you can do as part of your attack could be quite large, like 2 to the 60, right? So now you've got potentially a big number sitting here, which means you probably have to again make the group large, maybe even larger than you might otherwise need. So yes, you can get away with CDH with the simple change of just hashing the key, to create the key. But in the security sense, you get away with asking less of the group, but you probably have to use a larger group because of this term sitting out here, which you have really no control over as the security engineer. But in any case, you can actually build a public key encryption scheme out of a cyclic group and a hash function called hash elgamal, and it will be secure under the CDH assumption, given that the hash function is perfect. So now you have two different schemes. You have hashed elgamal and you have normal elgamal. One of them is provably secure from the DDH assumption. One of them is provably secure from the CDH assumption if you have a perfect hash function. That's kind of cool. You have your first two provably secure public key encryption schemes. We're going to see more, but we're going to see elgamal is important to see because it's sort of easy to understand, and it's easy to do the reduction down to DDH or CDH in the latter case. And it is used in some places, but more often than not, public key encryption, you don't end up using elgamal. You end up using standardized schemes like RSA-based OAEP, which we'll see in another lecture, or you use public key encryption schemes that are built from something called the ChemDem paradigm, key encapsulation mechanism, data encapsulation mechanism. And the idea there is basically use the public key part to encrypt a symmetric key and then send that along with the encryption of the actual plaintext under the symmetric key. This is a very common paradigm for using public key encryption, and we'll spend an entire lecture talking about that shortly.